What if the most resilient material you can possibly imagine, a mountain carved from a single flawless diamond, is in reality as fragile as spun sugar? What if the pinnacle of human engineering, a fortress built of tungsten steel and carbon composites, is, on a cosmic scale, as yielding as mist? We anchor our understanding of strength to the world we can touch, to the rock beneath our feet, to the metals we forge in fire. These are the paragons of endurance, the very definition of solid. Yet, in the silent, violent depths of the cosmos, the universe has forged a substance so fantastically strong, so utterly indomitable, that it makes a mockery of all our terrestrial standards. It is a material so far beyond our experience that it challenges the very laws of physics that describe our reality. To find it, we must leave behind everything we know about matter. We must abandon the familiar shores of atoms and molecules, of solids, liquids, and gases. We must undertake a journey to a place of such unimaginable violence and pressure that it represents the absolute boundary between existence and oblivion. Our destination is a cosmic graveyard, the collapsed heart of a giant exploded star. We're going inside a neutron star. From a distance it appears deceptively simple, a perfect sphere, barely 20 kilometers across, a city-sized remnant of a once mighty sun. It hangs in the blackness, a tiny hot cinder in the infinite void. But as we draw closer, this illusion of simplicity shatters into a billion complexities. The star's surface isn't a gentle globe, it's a terrifying alien landscape. We see a solid crust of iron nuclei, trapped in a crystalline lattice and swimming in a sea of hyper-energetic electrons. This isn't the iron of our world. It has been crushed by a gravitational force so immense, so utterly overpowering, that it has been polished to a near-perfect mirror, 10 million times smoother than any surface on Earth. The gravity here is a monster. 200 billion times stronger than our own planet's pull. It is a force that would not just crush you, but disassemble you, atom by atom. A single marshmallow, dropped from a height of 1 meter, would impact this surface with the force of 1,000 tons of TNT. Mountains, if they could even form, are flattened to mere millimeters in height, their constituent atoms screaming under the strain. This is a world defined by its gravitational tyranny, a cosmic vice tightening its grip with every passing moment. But the true wonders, the true terrors, lie beneath this tortured metallic shell. We must plunge deeper, through the crust into the star's enigmatic interior. The journey downwards is a descent into a new kind of physics, a realm where our intuition fails completely. Just a few meters below the solid surface, the pressure begins to build to levels that have no earthly equivalent. It exceeds the pressure at the core of our own sun by orders of magnitude, reaching a point where the fundamental structure of matter itself begins to buckle and break. We are entering a domain where the very building blocks of the universe are being systematically deconstructed and then violently repurposed. The atoms themselves, the indivisible units of classical science, are being squeezed to death. The immense gravitational pressure becomes a relentless hammer, forcing the star's electrons, which once orbited their atomic nuclei in graceful clouds, into a desperate suicidal plunge. They are driven directly into the protons at the heart of each nucleus. An electron and a proton, when forced together under such duress, undergo a miraculous and violent transformation. They merge, cancelling out their opposing charges, and become a single, neutral particle, a neutron. This process, known as neutronization, is the alchemical engine at the heart of the star. It is a continuous roaring cascade of atomic collapse, converting the star's substance from familiar elements into a super-dense, bizarre fluid, composed almost entirely of neutrons. This is the origin of the star's name, and it is the key to understanding the impossible material that lies hidden in its depths. As we sink deeper into this stellar core, we are surrounded by a sea of pure nuclear matter, a substance so dense that a single teaspoon of it would weigh over 1 billion tons on Earth. This is matter stripped of all its empty space, its atomic scaffolding torn away, leaving only the raw, naked nuclei packed together with unimaginable intimacy. The temperature soars to hundreds of millions of degrees, yet the material does not boil or expand. The crushing gravity holds it in a state of quantum degeneracy, a bizarre condition where the neutrons are packed so tightly that they behave less like individual particles and more like a single colossal quantum entity, atom. They are a fluid, but not like any fluid we know. It is a superfluid, flowing with absolutely zero viscosity, and a superconductor, conducting electricity with perfect efficiency. This neutron soup is the backdrop, the cosmic stage upon which the true drama is about to unfold. We continue our descent, reaching a strange and violent transition zone, a boundary layer between the outer crust and the deep inner core. Here, the pressure is catastrophic, but it has not yet reached the uniform, overwhelming totality of the star's heart. It is a place of tension, a battleground where two fundamental forces of nature are locked in a mortal struggle. On one side, there is gravity, the relentless compressor, fighting to squeeze every last bit of matter into a uniform, featureless singularity. On the other side, there is the nuclear strong force, the powerful glue that binds protons and neutrons together inside an atomic nucleus. This force, while incredibly powerful at short distances, resists being compressed beyond a certain point. It pushes back. And in this cosmic arm wrestle, in this precarious middle ground where neither force can claim absolute victory, something extraordinary and utterly alien is born. The neat spherical atomic nuclei which have survived the initial pressure finally begin to surrender their form. They are squeezed and distorted, stretched and flattened, forced to merge with their neighbours in a desperate attempt to withstand the gravitational onslaught. What emerges from this titanic conflict is not a simple fluid or a uniform solid. It is a grotesque, complex and eerily familiar collection of shapes. The universe, in its most extreme laboratory, has created pasta. Not the kind you eat, but a far more profound and fundamental version. This is nuclear pasta, and it is here, in this purgatorial layer of the neutron star, that we encounter what physicists believe to be the strongest material in the entire cosmos. As the density increases, the spherical nuclei, which physicists playfully call nuclear gnocchi, are the first to form, clumped together in the neutron sea. But as we go deeper still, the gnocchi are compressed further, fusing into long, tangled cylinders. We are now in the spaghetti phase. These are not microscopic strands, they are colossal structures on a nuclear scale, immensely dense and rigid filaments of nuclear matter, interwoven in a chaotic web. Deeper still, the pressure forces the spaghetti strands to merge into vast flat sheets, like colossal undulating planes of pure nuclear density. This is the lasagna phase. These are not simple layers, they are titanic, continent-sized plates of the universe's most robust substance, separated by thin voids filled with the neutron sea. The structure continues to mutate, with the voids themselves forming tubes in what is called the anti-spaghetti or bucatini phase, before finally dissolving into a uniform sea of neutrons in the deep core. This bizarre sequence, this cosmic culinary creation, is not mere speculation. It is the direct prediction of complex computer simulations, the logical outcome of pushing our best theories of nuclear physics to their absolute limits. And the properties of this material are staggering to contemplate. To break a piece of nuclear spaghetti, one would need to overcome the full, unbridled power of the nuclear strong force itself. This is the same force that holds the hearts of atoms together, the same energy unleashed in a thermonuclear explosion. Nuclear pasta is 10 billion times stronger than steel. It is a substance so tough, so resistant to stress and deformation that it redefines the very concept of strength. The forces required to snap it, to shear it, or to bend it are greater than any other known force in the universe, save for the gravity of a black hole. It is a material woven from the very fabric of nuclear reality, a crystalline lattice of pure force. It acts as a kind of skeletal framework for the neutron star's crust, creating irregularities, or mountains, on the star's surface. These pasta mountains, though perhaps only centimeters high, are so massive and so dense that their spinning creates ripples in the fabric of space-time itself, gravitational waves that we are only now beginning to detect here on Earth. So we are left standing at the edge of a profound mystery, gazing into the heart of a cosmic crucible. We have journeyed to a place where matter behaves in ways that defy all earthly comparison, where gravity and nuclear physics wage a war that results in the creation of the universe's ultimate supermaterial. But what does this truly mean? How can something so ephemeral sounding as pasta possess such monumental strength? What are the precise mechanics that give these bizarre structures their incredible resilience? Is it merely their density, or is there some deeper quantum mechanical principle at work, a secret architecture of force that we have yet to fully comprehend? And what can this alien substance teach us about the universe itself? By studying nuclear pasta, can we unlock new insights into the behaviour of matter under the most extreme conditions imaginable? Can it help us understand the final, violent moments of a star's life, or the ripples in space-time that carry its secrets across the light years? The questions are as vast and as deep as the cosmos itself. The answers are buried a kilometre deep inside the densest object we can see, a place we can never hope to visit. But through the power of physics, through the language of mathematics and the ingenuity of simulation, we can begin to peel back the layers of this celestial enigma. We can reach into that stellar furnace and for the first time begin to understand the true nature of nuclear pasta, the strongest material in the universe. What if the most indestructible substance in the universe is not built, but broken? What if true strength, on a scale that defies all human imagination, is not the product of careful design, but of unimaginable violence? We spend our lives engineering materials to be stronger, lighter, more resilient. We forge steel in fire, weave carbon into composites, and dream of structures that can withstand the tests of time. Yet all our achievements, all our clever designs, are but fragile whispers against the roar of the cosmos. Out there in the graveyards of giants, the universe has already forged a material so profoundly strong, so ridiculously dense, that it makes diamonds seem as soft as clay. It is a substance born not in a laboratory, but in the heart of a stellar apocalypse. And to understand its existence, we must first bear witness to one of the most spectacular events in creation, the death of a star. Our journey begins with a titan, a celestial behemoth, at least 8 times more massive than our own sun. For millions of years, this star has been a brilliant, self-sustaining nuclear furnace, a radiant beacon in the cosmic dark. Deep within its core, a constant battle rages, a perfect and delicate equilibrium between two monumental forces. On one side, there is the relentless crush of gravity, the star's own immense mass pulling every single particle inward in a desperate attempt to collapse upon itself. On the other, the outward blast of nuclear fusion, a continuous chain of thermonuclear explosions converting hydrogen into helium, and then helium into heavier and heavier elements. This thermonuclear heartbeat, this radiant pressure, is the only thing holding the star up against its own colossal weight. For eons, this cosmic balancing act defines the star's life, a stable and shining existence fueled by the transmutation of elements. It forges the carbon of our cells, the oxygen we breathe, the silicon of the rocks beneath our feet, creating a cascade of new atomic nuclei in a forge of unimaginable temperature and pressure. But this process cannot last forever. The star's life is a story written in its fuel, and eventually that fuel begins to run out. As the core synthesizes progressively heavier elements, neon, magnesium, sulfur, each successive reaction provides less and less energy. The star's heartbeat becomes weaker, more frantic. The gravitational pressure, ever present and unforgiving, begins to gain the upper hand. The core shrinks, heats up, and desperately ignites the next, heavier element in its arsenal, buying itself a temporary reprieve. This is the star's frantic old age, a series of violent, shuddering adjustments against the inevitable. Finally, the fusion process reaches its ultimate dead end: iron. Iron is cosmic ash. Fusing iron atoms into anything heavier does not release energy. It consumes it. The thermonuclear heart of the star, the engine that has held gravity at bay for millions of years, suddenly and catastrophically ceases to beat. In less than a second, the equilibrium that defined the star's entire existence is shattered. With no outward pressure to support it, gravity wins, it wins instantly and absolutely. The star's iron core, an object already the size of our Earth, but containing the mass of 1.5 suns, begins to collapse. What follows is not a gentle settling, but a cataclysmic implosion of staggering speed. The outer layers of the core plummet inward at nearly 1/4 of the speed of light, a torrential rain of matter converging on a single point. The temperature and density skyrocket to levels that defy comprehension. We're no longer dealing with the familiar physics of gas or plasma. We're in a realm where the very structure of the atom, the fundamental building block of our reality, is about to be annihilated. The sheer pressure becomes so intense that it overcomes one of the most fundamental forces of nature, the electron degeneracy pressure. This is the quantum mechanical rule that prevents 2 electrons from occupying the same state in the same space. It is the very force that makes solid matter solid, the reason your hand doesn't pass straight through your desk. In the collapsing core of the star, this fundamental barrier is broken. The gravitational vice becomes so powerful that electrons are literally squeezed into the protons within the iron nuclei. An electron and a proton, a negative and a positive charge, are forced to merge, cancelling each other out to become a single, neutral particle, a neutron. This process, called inverse beta decay, happens everywhere in the core at once. The atomic structure of matter dissolves. The space within atoms, the vast emptiness that makes up over 99% of everything we know, simply vanishes. A sphere of iron the size of a planet is crushed down into a ball of pure neutrons no larger than a city. This new, ultra-dense core is incompressible, a solid wall of nuclear matter. The material that was still raining down from the star's outer layers, travelling at unimaginable speeds, slams into this newly formed, unyielding surface. The result is the most powerful shockwave in the universe. The infalling material rebounds off the neutron core with titanic force, creating a supersonic wave of energy that screams back out through the star's remaining layers. This shockwave, supercharged by a flood of ghostly particles called neutrinos, released during the neutron formation, carries with it all the heavy elements forged during the star's life. It rips the star apart from the inside out in a final, glorious act of self-destruction. This is a supernova, an explosion so luminous it can briefly outshine its entire host galaxy, a celestial exclamation point visible across billions of light years. For a few brilliant weeks it burns with the light of 100 billion suns, seeding the cosmos with the raw materials for future stars, future planets, and perhaps future life. It is the ultimate act of cosmic recycling, a violent death that is also a spectacular act of creation. But after the light fades, after the shockwave has dissipated and the beautiful expanding nebula of gas and dust has thinned into the interstellar void, something remains. Hiding amidst the fading embers of the explosion is the author of this destruction, the crushed and compacted heart of the dead star. What is left behind is one of the most extreme and enigmatic objects in the entire universe, a neutron star. This is the stellar corpse, the ghost of the departed Titan. And it is here, within this tiny, bizarre remnant, that our quest for the universe's strongest material truly begins. To call a neutron star dense is a profound understatement. Imagine taking our Sun, a star so vast that you could fit over 1 million Earths inside it, and compressing it down into a sphere barely 12 miles across. Imagine the entire human race, all 8 billion of us, squeezed into the volume of a single sugar cube. A mere teaspoon of neutron star material would have a mass of over 5 billion tons, equivalent to the weight of Mount Everest. This is matter at the absolute edge of existence, pushed to the very brink of collapsing into a black hole. Its properties are so far removed from our everyday experience that they sound like science fiction. Its surface gravity is hundreds of billions of times stronger than Earth's. If you were to drop an object from just a meter above its surface, it would impact in a single microsecond, hitting with the force of a nuclear bomb. The immense gravitational field warps the very fabric of space-time around it so severely that light itself is bent, allowing us to see parts of the star's back surface. Furthermore, as the original star's core collapsed, it conserved its angular momentum much like an ice skater pulling in their arms to spin faster. This dramatic reduction in size spins the neutron star up to incredible rotational speeds. Many of these cosmic gyroscopes rotate hundreds of times every single second, their powerful magnetic fields, also concentrated by the collapse, sweeping through space like a lighthouse beam, creating the pulsars that radio astronomers detect from Earth. But to find the secrets we seek, we must venture beyond these astonishing external properties. We must journey inside through the layers of this celestial artifact into a realm where the laws of physics are rewritten. Imagine you could construct a vessel capable of withstanding the ludicrous gravity and radiation, a craft to descend through the neutron star's thin atmosphere of superheated plasma. Just a few meters below this gaseous veil, the journey would become truly alien. The pressure is already so immense that it solidifies the surface into a crust. But this is no ordinary solid. The atoms here are crushed into a state of near-perfect order. The immense gravitational field has stripped most of the electrons away from their atomic nuclei, leaving behind a sea of free-flowing electrons moving among a rigid grid of heavy, neutron-rich ions like iron. This is a crystalline solid, a metallic lattice of extraordinary rigidity. It's a structure governed by the mutual repulsion of the positively charged nuclei, which arrange themselves into the most energy-efficient pattern possible, a perfectly ordered crystal structure known as a Coulomb crystal. This outer crust is already staggeringly strong, thousands of times more resistant to breaking than the strongest steel ever produced on Earth. But this is just the beginning of our descent. As we travel deeper, perhaps a kilometre down into the inner crust, the pressure continues to mount to truly insane levels. We are entering a region where the force of gravity is so overwhelming that it begins to wage war on the atomic nuclei themselves. The stable iron nuclei that form the lattice of the outer crust can no longer survive. The pressure is so great that it becomes energetically favourable for the nuclei to absorb more and more of the high-energy electrons from the surrounding sea. Protons within the nuclei continue their transformation into neutrons. The nuclei become bloated, engorged with an unnatural surplus of neutrons, forming exotic isotopes that would be impossibly unstable anywhere else in the universe. They are held together only by the suffocating grip of the ambient pressure. This is where the familiar world of physics, the world of solids, liquids and gases that we learn about in school, completely and utterly breaks down. We have a word for the state of matter in the core of our sun: plasma, a superheated soup of disconnected ions and electrons. We understand the crystalline lattice of a solid diamond, the free-flowing nature of liquid water, the diffuse chaos of a gas. For centuries, these states of matter have defined our understanding of the physical world. They are the pillars of chemistry and material science, the foundation upon which we have built our civilization. Yet here, in the inner crust of a neutron star, we encounter a profound and daunting mystery. We have reached a theoretical wall, a point where our terrestrial intuition fails us entirely. The pressure has become so great, and the nuclei so saturated with neutrons, that something new must happen. Physicists wrestling with this problem in the mid-20th century found themselves in uncharted territory. The models that worked so well for describing planets, stars, and even the bizarre physics of white dwarfs began to produce nonsensical results when applied to this unique environment. The nuclei, pushed to their absolute breaking point, would eventually begin to dissolve. Neutrons, no longer content to be confined within an atomic nucleus, would start to drip out, leaking into the spaces between the lattice points and forming a superfluid gas. Now you have a mixture of two phases of matter existing simultaneously: the rigid lattice of gargantuan, deformed nuclei, and a frictionless sea of free-flowing neutrons swirling around them. This is a situation with no earthly parallel. How would these two components interact? What kind of structure would they form? As we push deeper still, the density increases even further. The nuclei are forced closer and closer together by the ever-increasing gravitational squeeze. At some critical point, the repulsive electrical force that keeps these positively charged nuclei apart in their neat crystal lattice can no longer hold them at a distance. They begin to touch. They begin to merge. The very concept of an individual atomic nucleus, the central tenet of chemistry for over a century ceases to have meaning. The entire system is on the verge of transforming into something utterly new, a frustrated state of matter caught between the ordered structure of a solid crystal and the uniform soup of the neutron star's liquid core. What shape does nuclear matter take when it is stretched, squeezed, and deformed in this cosmic crucible? What happens when protons and neutrons, the very bedrock of our existence, are forced to assemble themselves into new and monstrous configurations under pressures that our minds can barely grasp? It was this very question that led scientists to a startling and bizarre revelation, a new phase of matter so strange, so exotic, that it was named after a common food. The stage was set for the discovery of a substance that would redefine the limits of physical strength, a material forged in the twilight zone between order and chaos. Beyond the star's crystalline outer shell, where the atoms we know have long been annihilated, we descend into a realm of pure theoretical physics. Here, in this cosmic pressure cooker, the simple model of a uniform sea of neutrons and protons begins to fray at the edges, inadequate for the sheer violence of the environment. The elegant mathematics that describe the outer layers starts to produce nonsensical answers, hinting that something far more complex, far more alien, was lurking deeper within. For decades, our understanding of a neutron star's crust was built on a foundational assumption that under enough pressure, matter would simply arrange itself into the most efficient shape possible. And in the universe, that shape is almost always a sphere. It's the default geometry of physics, from raindrops to planets to stars. Spheres minimize surface area, they distribute forces evenly, they are the path of least resistance. So naturally, scientists assumed that the protons and neutrons deep inside the crust would clump together into spherical nuclei, just unimaginably dense ones, swimming in a gas of liberated electrons. This was a clean, orderly picture, but it was also, as it turned out, profoundly wrong. The universe, especially at its extremes, rarely settles for simple elegance when it can achieve baroque complexity. The first clues that our picture was incomplete emerged not from telescopes, but from the quiet hum of supercomputers. Physicists like Charles Horowitz and James Latimer began creating increasingly sophisticated models, attempting to simulate this sliver of the neutron star crust just a few hundred meters thick. They were trying to solve a puzzle governed by two titanic warring forces. On one side, you have the strong nuclear force, the most powerful force in creation. It is the cosmic superglue that binds protons and neutrons together into atomic nuclei. Its pull is ferocious, desperate to gather nucleons into the tightest, most stable configurations possible. In the crushing environment of the neutron star, it yearns to form large, dense spheres of nuclear matter. But fighting against it is a more familiar, yet relentlessly stubborn adversary: the electromagnetic force, specifically the Coulomb repulsion between positively charged protons. Like magnets of the same polarity pushed together, protons want nothing more than to fly apart. In a normal atomic nucleus on Earth, the strong force easily overpowers this repulsion, holding the core together. But here, the game has changed entirely. The gravitational pressure is so immense that it is forcing tens, then hundreds of protons into the same tiny volume. The repulsive electromagnetic energy builds to an insane degree, a coiled spring of pure electrostatic rage. The two fundamental forces become locked in a cosmic stalemate, a quantum tug-of-war on a scale that defies all human experience. The strong force pulls inward, trying to build a perfect sphere. The Coulomb force pushes outward, trying to tear that sphere apart from the inside. This is the central conflict, the dramatic engine that drives the creation of the universe's most exotic material. As the simulations ran, crunching calculations for weeks on end, they revealed a startling compromise. The matter found a way to satisfy both masters. It discovered that if it couldn't form a perfect sphere, it could instead build something else entirely, something long and thin, or something flat and wide, structures that would allow the strong force to keep the nucleons bound together in a dense state, while simultaneously maximizing the distance between the repulsive protons, thereby lowering the crippling electrostatic energy. The system, in a moment of profound physical insight, chose geometry as its escape valve. the neat, orderly picture of spherical nuclei dissolved into chaos. And from that chaos, a new, bizarre order began to emerge on the computer screens. At first, the scientists thought it must be a glitch, a bug in the code. What their models were showing them looked less like the interior of a star and more like something from a subatomic kitchen. In the upper layers of this strange domain, just below the outer crust, the nuclei began to stretch. The familiar spheres, under the immense strain, elongated into long, stringy filaments of nuclear density matter, all tangled together like spaghetti. Thousands upon thousands of these quantum threads, each one trillions of times denser than lead, would form a complex interconnected web, surrounded by a gas of free-flowing neutrons. The physicists were staring at a prediction of nuclear spaghetti. It was a structure so profoundly weird, so contrary to intuition, that it felt like science fiction, yet the calculations were undeniable. This configuration, this long string-like arrangement, was energetically favourable. It was the lowest energy state. It was what nature would do. The initial reaction in the astrophysics community was a fascinating cocktail of deep skepticism and giddy excitement. The name itself, nuclear pasta, coined in the early papers by researchers like D.G. Ravenhall and C.J. Pethick, was both a blessing and a curse. It was playful, instantly memorable, and perfectly descriptive of the shapes the computers were predicting. It made an arcane concept in nuclear physics immediately accessible, but that same playfulness also made it sound to some less than serious. Was this a genuine prediction about the fundamental state of matter, or was it just a colourful name for a computational artifact, a ghost in the machine that would vanish with better models? The debate began to simmer. For some, it was a breakthrough, a profound insight into how matter behaves when pushed beyond all terrestrial limits. It suggested that neutron stars were not just simple, uniform balls of neutrons, but had a rich and complex internal geology. For the skeptics, however, it was a step too far. The models, they argued, were still too simplistic. They had to make approximations about the interactions between hundreds of thousands of individual particles. How could we be sure that these intricate shapes weren't just a consequence of those approximations? How could we trust a simulation to tell us about a place we could never, ever visit? It was a valid and crucial scientific question. The burden of proof was on the theorists. They had to demonstrate that this wasn't just a fantasy born of silicon and code. They had to show that nuclear pasta was an inevitable consequence of the laws of physics. So they refined their models, increased their computational power, and pushed their simulations to new levels of fidelity, scrutinizing every variable and every assumption. They subjected their digital universes to every test they could devise, trying to break the result, trying to make the pasta faces disappear. But the pasta refused to vanish. In fact, as the models grew more powerful and sophisticated, the structures became even more defined, more robust, more varied. The simulations revealed that as you descend deeper into the crust, the density continues to increase and the cosmic recipe changes. The spaghetti phase, those long nuclear filaments, eventually finds itself under too much pressure. The strings are squeezed closer and closer together until they begin to merge. They fuse into vast parallel sheets of nuclear matter, separated by layers of neutron gas. The star, in its deeper layers, was predicted to be building nuclear lasagna. Imagine continent-sized plates of the densest material in existence, stacked one on top of another, forming a colossal layered scaffold inside the star. This structure once again represented a brilliant compromise, a new way for matter to organize itself to minimize the energy of that relentless battle between the forces. And the journey didn't end there. As the models pushed even deeper, approaching the boundary with the star's core, the roles of matter and empty space began to invert. In the upper pasta layers, you have dense structures, the spaghetti or the lasagna residing in a sea of lower density neutron gas. But at a critical point, the density of the neutron gas becomes so high that it becomes the dominant component. The nuclear matter, which once formed the structures, now becomes the empty space. Instead of dense strings in a gas, you get gaseous tunnels boring through a solid block of nuclear matter. This is the anti-spaghetti or bucatini phase, and instead of dense sheets, you get liquid layers trapped between solid walls of nuclear matter, a kind of anti-lasagna. The very definition of structure and void flips on its head. It's a concept so disorienting it challenges our fundamental perception of what it means to be solid. Between these major phases, the simulations predicted even more exotic transitional geometries. As the spaghetti strands merge to form lasagna sheets, they might first clump together into pockets of dense matter, disconnected from one another. These blobs, roughly spherical, would arrange themselves in the neutron gas, looking for all the world like nuclear gnocchi. And as the lasagna sheets begin to break down into the inverted tunnel-like phases, they might first develop holes, creating a grid-like structure of interconnected dense columns and empty neutron gas voids. This phase, a sort of three-dimensional lattice, was dubbed nuclear waffle. The sheer variety was breathtaking. It wasn't just one strange new form of matter, but a whole sequence of them, a cascade of phase transitions that transformed the star's crust into a landscape of unimaginable complexity and structure. This theoretical prediction represented a paradigm shift. If true, the crust of a neutron star was not a simple boundary layer. It was a dynamic, structured component of the star in its own right, a region with a bizarre alien geology that could have profound consequences for the star's overall behaviour. The excitement among its proponents was palpable. Suddenly, a whole host of previously unexplained neutron star phenomena had a potential cause. For example, astronomers had observed glitches in the rotation of pulsars. These are sudden, tiny accelerations in the star's otherwise incredibly precise spin. A perfectly smooth fluid star shouldn't do that. But a star with a solid, structured, and potentially brittle crust. A crust made of nuclear lasagna. Perhaps that crust could build up stress over time and then suddenly crack, like tectonic plates on Earth, causing the star to shudder and spin up slightly. Nuclear pasta provided a beautiful, compelling physical mechanism for these mysterious glitches. Furthermore, the pasta could dramatically alter how the star cools. A uniform sea of neutrons would transport heat in a predictable way. But a crust filled with tangled spaghetti or stacked lasagna sheets would be highly anisotropic, meaning it would conduct heat differently in different directions. Heat might flow easily along the spaghetti strands, or across the lasagna sheets but struggle to move between them. This complex thermal conductivity would directly influence the star's surface temperature, something our telescopes can actually measure. By observing how neutron stars cool over millions of years, we could potentially see the thermal signature of the pasta hidden deep below. The theory was no longer just a computational curiosity, it was making testable predictions. It was offering solutions to long-standing astronomical puzzles, connecting the unimaginably small world of subatomic physics to the colossal scale of stellar evolution. The blend of skepticism and excitement created a fertile ground for new research. It forced physicists to sharpen their tools, to confront the limitations of their models, and to think more creatively about how matter could possibly behave under such duress. The idea of nuclear pasta stretched the imagination, but it was born from the rigorous application of the known laws of physics. It wasn't magic. It was the logical, albeit shocking conclusion of pushing quantum mechanics and general relativity to their absolute limits. The community was faced with a profound question. Did the universe really build these intricate, beautiful, and utterly alien structures in the hearts of dead stars? Was there truly a place just a few thousand light years away where matter mimicked the forms of our most humble foods, yet was forged with the power of a supernova? Theorists began to think about the next step. If this stuff exists, what are its properties? How strong would it be? We had already established that the outer crust was strong, but this pasta, with its interconnected and complex geometries, promised to be something else entirely. It wasn't just a collection of individual nuclei anymore. It was a single, continuous macroscopic quantum object. The spaghetti strands weren't just floating near each other, they were likely fused into a single, tangled, continent-spanning structure. The lasagna sheets weren't just stacked, they were part of a monolithic, planet-sized crystal. The implications were staggering. If you could somehow reach in and pull on one strand of nuclear spaghetti, you would be pulling on the entire crust of the star. This realization began to dawn on the scientific community. They weren't just talking about a new state of matter, they were talking about the potential existence of the strongest material in the entire universe. A material whose strength and resilience would not be measured by the familiar forces of chemical bonds that hold steel or diamond together, but by the raw, untamed power of the strong nuclear force itself. The playful name belied a terrifying reality. This substance would be so durable, so resistant to deformation, that it would make all other materials in the cosmos seem as fragile as smoke. The quest was no longer just to prove that nuclear pasta existed. The quest was now to understand the true nature of this predicted supermaterial, to calculate its properties, and to figure out what a mountain range made of nuclear lasagna could possibly mean for the life and death of a star. The door had been opened to a new frontier of physics, and beyond it lay a landscape more wondrous and more violent than anyone had ever dared to imagine. We have journeyed deep into the heart of a fallen star, venturing through its crushing gravity into a subatomic realm where the very rules of matter are rewritten. We have witnessed the great cosmic compromise, the desperate balancing act between the forces of repulsion and attraction that sculpts protons and neutrons into a gallery of alien shapes. We have seen the gnocchi, the spaghetti, the lasagna of the cosmos, a bizarre celestial pasta bar cooked under impossible pressures. For decades, this was a triumph of theoretical physics, a strange, beautiful, but ultimately abstract prediction. It was a wonder of the mind, a ghost haunting our equations. The question that lingered, the one that kept theorists awake at night, was not merely what these structures looked like, but what they were truly like. How would this phantom material behave if you could reach out and touch it? If you could take a slab of this nuclear lasagna and try to bend it, what would happen? The inquiry seemed almost whimsical, a physicist's daydream, but the answer, when it finally began to emerge, was anything but. It would trigger a profound re-evaluation of neutron stars themselves, transforming them in our understanding from simple, passive cinders into dynamic, violent objects of terrifying power. The revolution didn't begin in an observatory staring through a telescope. It couldn't. This world is forever veiled from our direct sight, locked away a mile beneath a star's surface. No, this discovery was forged in the disembodied universe of the machine, inside the humming, silent cathedrals of supercomputers. Physicists needed to build a virtual neutron star crust, a digital crucible where they could torment nuclear pasta and measure its response. This was a task of Herculean, almost ludicrous complexity. You can't simulate a handful of protons and neutrons using simple mechanics, like billiard balls bouncing off one another. Every single particle is a phantom of quantum probability, a complex dance of wave functions governed by the strong nuclear force, the most powerful and least understood of nature's fundamental forces. To model even a microscopic cube of this material, a fragment smaller than a single atomic nucleus on Earth, required tracking the intricate quantum interactions of tens of thousands of individual nucleons. The computational cost was staggering. It was a demand that would have buckled the world's most powerful computers just a few years prior. But as computational power grew exponentially, following the relentless rhythm of Moore's law, what was once impossible became merely monstrously difficult. Teams of physicists and computer scientists began to build their virtual labs. They would write millions of lines of code, creating bespoke universes governed by the laws of quantum chromodynamics. Inside these digital realms, they could meticulously arrange protons and neutrons, squeeze them together with simulated gravity, and watch as they spontaneously self-assembled into the familiar pasta shapes. Then, with the ghostly architecture in place, they began the real experiment. They started to push on it. They applied a virtual stress, a shear force, attempting to deform the delicate lattice of nuclear spaghetti, to slide one layer of nuclear lasagna over another. And the simulation resisted. It resisted with a ferocity that seemed to defy all logic. The numbers that streamed out of these early simulations were so extreme, so utterly beyond the pale of known material science, that the first reaction of the research teams was disbelief. There had to be a mistake, a bug in the code, an error in the physical model, a fundamental miscalculation somewhere in the chain of logic. Materials simply did not, could not, behave this way. So they refined their models. They ran the simulations again on different supercomputers. Rival teams working independently across the globe developed their own code from scratch, trying to prove the initial results wrong. Yet, with every new dataset, with every cross-check and verification, the same impossible truth stared back at them from the screen. The conclusion was inescapable. Nuclear pasta was not just strong, it was an entirely new regime of strength, a form of material resilience so far beyond our terrestrial experience that we lack the proper language to truly describe it. To understand the scale of this discovery, we need to think about how we measure strength here on Earth. When we test a material, we're often interested in its rigidity, its resistance to being bent or twisted out of shape. This property is known as the shear modulus. Imagine trying to slide the cover of a book horizontally without lifting it off the pages. The force required to make the cover move, to shear it across the pages, is a measure of the friction and the book's structural integrity. Now, imagine the book is a solid block of steel. The force required to shear the top layer of atoms even a tiny fraction of an inch across the bottom layer is immense. Steel, the backbone of our civilization, the material we use to build skyscrapers and bridges, is defined by this rigidity. It is our benchmark for brute strength. But the simulations were showing that to shear a block of nuclear pasta, to make one sheet of the lasagna slide across its neighbour, you would need to apply a force 10 billion times greater than what is needed to shear an equivalent block of steel. 10 billion. Let that number sink in. It's a scale of difference that breaks all our intuition. It is the difference between the gentle tap of a finger and the full sustained thrust of a Saturn V rocket engine. It is the difference between the weight of a single grain of sand and the weight of the entire Great Pyramid of Giza. But even steel isn't the ultimate champion of earthly materials. What about diamond, the hardest substance known in nature? Or graphene, the single atom-thick sheet of carbon, the miracle material theoretically stronger than diamond? These are the pinnacles of molecular engineering, their atoms locked in perfect, unyielding covalent bonds. Surely this strange nuclear matter couldn't compete with them, but it does, and it leaves them in the dust. Nuclear pasta is over 100 million times more resistant to shearing than carbon steel. It is tens of millions of times more rigid than diamond. It makes graphene, the supposed strongest material possible, look like fragile parchment by comparison. This isn't just a quantitative leap, it's a qualitative one. It's like discovering a creature that can run faster than the speed of a light. It fundamentally breaks the known scale. The scientific community was grappling with a revelation. They had found the strongest material in the entire universe. And the reason for its unbelievable power lies in the very nature of its construction. Every material you have ever encountered owes its strength to the electromagnetic force. The bonds between atoms in a diamond crystal, the metallic bonds in a girder of steel, these are all products of electrons being shared and exchanged, a cosmic glue generated by particles orbiting the atomic nucleus. But in nuclear pasta, the electrons are gone. They have been crushed into protons to form more neutrons, leaving behind a sea of unbound, degenerate electrons that contributes almost nothing to the structural integrity. The binding force here is not electromagnetism. It is the strong nuclear force itself, the same primordial power that holds protons and neutrons together inside an atomic nucleus. The force that overcomes the immense repulsion of positively charged protons is acting on a macroscopic scale. The nuclear spaghetti is not a molecule. It is effectively a single, continuous, continent-sized atomic nucleus. The sheets of lasagna are not layers of atoms. They are colossal, two-dimensional nuclei bound together by the residual echoes of that same indomitable force. To break nuclear pasta is not to snap a chemical bond. It is to attempt to rip apart the very fabric of an atomic nucleus. You are fighting against the most powerful of nature's four fundamental forces, and that force does not yield. This discovery fundamentally changed our picture of a neutron star. Before, the dominant model treated the star's crust as a kind of fluid crystal, strong, yes, but ultimately something that could flow and deform under the star's immense gravitational stresses. It was seen as a relatively smooth, passive shell over a liquid interior. But these simulations revealed something far more dramatic. The crust of a neutron star is not a simple shell. It is a solid, structured, load-bearing component of unimaginable strength. It is a planetary-scale crystal lattice forged from nuclear matter, a rigid framework capable of withstanding and storing incomprehensible amounts of stress. The star, we now realised, has a solid skeleton. This transition in thinking was as profound as the moment geologists realised Earth's surface wasn't a static crust, but a dynamic system of tectonic plates grinding against each other. The neutron star was no longer a perfect, featureless sphere. It was a geological world, a world with topography. The immense strength of the nuclear pasta crust means it can support enormous structures, what we now call neutron star mountains. These are not mountains of rock and ice like we have on Earth. They are subtle, solid-state distortions in the star's shape, perhaps only centimetres high, but composed of this ultra-rigid material. And because the neutron star is spinning hundreds of times per second, these tiny mountain-like imperfections act as gravitational hammers, constantly whipping through space-time and flinging out ripples. They are gravitational beacons, broadcasting the secrets of the star's interior across the cosmos in the form of continuous gravitational waves. Suddenly, we had a new way to see these invisible objects, a new physical mechanism to hunt for with our detectors. The strange pasta shapes were not just a curiosity, they were the key to the star's entire geophysical life. They were the bedrock of its landscape, the source of its gravitational voice. This realization, born in the heart of a supercomputer, opened up a cascade of even more tantalizing and terrifying questions. We had established the crust's almost limitless strength. We had proven its ability to resist deformation to a godlike degree, but nothing is infinite. Every structure, no matter how strong, has a breaking point. The star's colossal magnetic field and its turbulent interior are constantly stressing this rigid crust, twisting and pulling on it with forces that beggar the imagination. So the next, unavoidable question became the most dramatic of all. What happens when a structure 10 billion times stronger than steel, a solid crust forged from the most powerful force in the universe, is finally pushed beyond its limit? What happens when the strongest material in the cosmos cracks? Having now quantified its colossal strength, a stiffness that shatters every terrestrial record and defies our earthbound intuition, we are left with a profound question. What does it mean for something this powerful to exist? A number on a page, however staggering, is merely the shadow of the truth. The real story, the epic narrative of nuclear pasta, only truly begins when we take this impossible material and place it back where it belongs, deep beneath the crystalline crust of a neutron star, inside the most violent and compressed celestial furnace in the known universe. Here, in this crucible of cosmic forces, its theoretical strength is no longer an academic curiosity. It becomes a defining feature of stellar evolution, a gravitational anchor shaping the very destiny of these stellar corpses. Its presence transforms a neutron star from a simple, uniform sphere of crushed matter into a complex geological world, one with a hidden skeletal structure capable of altering the symphony of spacetime itself. Imagine two such stars locked in a gravitational death spiral. They are cosmic twins, each packing more than the sun's mass into a sphere barely the size of a city. For millions of years they have waltzed across the void, orbiting one another in an ever-tightening embrace. As they draw closer, the forces at play become monstrous. Gravity, the silent sculptor of galaxies, becomes a weapon of cosmic annihilation. Each star begins to feel the tidal pull of its companion, a relentless stretching and squeezing that would tear any normal object to shreds. A planet, an ordinary star, even a white dwarf would be unraveled into a stream of incandescent gas, its substance smeared across its partner's gravitational field. This is the Roche limit, the point of no return where an object's own gravity can no longer hold it together. We expect a neutron star's solid outer crust, a lattice of iron and other heavy nuclei, to resist. But even this crust, 1 billion times stronger than steel, has its breaking point. Under the relentless gravitational assault of an approaching sibling, this crust should crack, shatter, and ultimately liquefy, allowing the star to deform, to bulge towards its tormentor like a teardrop of neutronium. This deformation is critical. It determines the precise rhythm of their final dance, the exact timing and frequency of the gravitational waves they churn out into the universe. Yet, our models, when they account for the bizarre physics of the deep interior, hint at a different story. They suggest the star holds its shape with an almost supernatural rigidity, far longer and more stubbornly than it has any right to. The reason, we believe, is hidden just a few hundred meters below that fracturing iron surface. Here lies the pasta, not as a simple layer, but as a vast, three-dimensional, interconnected scaffolding of unimaginable tenacity. The gnocchi, the spaghetti, the lasagna, these faces are not just stacked, they are fused into a single, continuous continent-spanning structure of pure nuclear matter. This is the star's secret skeleton. When the companion star pulls, it isn't just tugging on a brittle outer shell, it is pulling against this monolithic pasta-reinforced superstructure. The immense stiffness we calculated in our supercomputers now plays out on a celestial stage. The pasta acts as a cosmic rebar, a structural reinforcement that resists the tidal shearing and prevents the star from being easily distorted. It maintains the star's spherical integrity against forces that could literally rip space-time apart. For precious milliseconds longer, the star holds its ground, a perfect sphere against all cosmic logic, a testament to the binding power of the strong nuclear force. This stubborn refusal to yield has profound consequences, not just for the star, but for us, the distant observers trying to decipher the secrets of its final, cataclysmic moments. This same internal fortitude has an equally dramatic effect on the star's own internal life. Neutron stars, for all their density, are not static objects. They are dynamic, evolving, and incredibly violent. As a young neutron star spins, it gradually slows down, its rotational energy bleeding away into space. This slowdown forces its shape to become more spherical, but its crust is solid, rigid. It resists this change. Tension builds within the crust, accumulating over centuries, even millennia. The strain mounts year after year, until the crust can no longer bear the load. It reaches a breaking point. Suddenly, and catastrophically, a section of the crust cracks and buckles, collapsing inward by perhaps a mere millimeter. This is a starquake. To call it a quake is a profound understatement. A millimeter shift of a neutron star's crust releases more energy than 100 million of our sun's solar flares. The star's entire magnetic field can be violently reconfigured in an instant, unleashing a blinding flash of gamma rays, a magnetar flare that can be detected halfway across the galaxy. The star itself rings like a colossal bell, vibrating with seismic waves that churn the neutron superfluid deep within its core. These events, these sudden violent ruptures, were thought to be a fundamental part of a neutron star's life cycle, a key mechanism in how it aged and shed its incredible energy. But this model assumes a crust that is merely strong. It does not account for a crust that is impossibly strong, a crust undergirded by the strange geometries of nuclear pasta. If a thick layer of nuclear pasta truly exists, it would act as the ultimate seismic dampener. Think of the difference between a sheet of brittle glass and a sheet of shatterproof laminated glass. The ordinary crust is the single pane of glass. When the stress becomes too great, it fails catastrophically in a single explosive event. The nuclear pasta, however, is the lamination. Its complex interconnected structures, the rods of spaghetti, the sheets of lasagna, are capable of absorbing and redistributing stress in ways a simple crystal lattice cannot. Instead of the tension building up in one localized region to a single breaking point, the pasta layer can dissipate that strain across its entire volume. It can flow, bend, and rearrange itself on a microscopic level, accommodating the star's changing shape gradually and smoothly. This changes everything. A star with a significant pasta layer might not experience the titanic explosive starquakes we once predicted. Instead of sudden violent cracks, it would undergo a series of countless tiny imperceptible adjustments. The settling of the crust becomes less like an earthquake and more like the slow, steady creep of a glacier. This would dramatically alter how the star cools over cosmic time and how its magnetic field evolves. The cataclysmic gamma-ray flares from magnetars, some of the most energetic events in the universe, might only be possible if the pasta layer is thin or absent, allowing the brittle outer crust to build up enough stress to fail so spectacularly. The presence, or absence, of nuclear pasta could be the single deciding factor that separates a quiet neutron star from a raging incandescent magnetar. It is the hidden geology that dictates the star's planetary scale weather. These two consequences, the resistance to tidal forces and the suppression of starquakes, are not just theoretical curiosities. They converge at the most dramatic event a neutron star can experience, a binary merger. For the last decade, we have opened a new window onto the universe, the ability to hear the vibrations of space-time itself. When two neutron stars finally collide, they send out a powerful burst of gravitational waves, a cosmic chirp that carries with it an exquisitely detailed account of their final moments. And in that final fraction of a second, as the two stars are tidally deformed and then ripped apart, the properties of their matter are imprinted onto the outgoing gravitational wave signal. The frequency, the amplitude, the very shape of that waveform is a direct message from the heart of the collision, and this is where nuclear pasta may finally reveal itself. A neutron star with a weak, easily deformable crust would begin to stretch and tear early in the merger process. This preemptive destruction would be encoded in the gravitational waves, a specific modulation in the signal's frequency climb. But a star reinforced by a super stiff pasta skeleton would resist. It would hold its spherical shape until the last possible microsecond. Its final moments would be less of a graceful shredding and more of a sudden, violent shattering. This difference, the signature of a stiff crust versus a soft one, would produce a subtly but detectably different gravitational wave signal. The chirp would have a slightly higher pitch just before the final crescendo, a tiny deviation in the cosmic score that would tell us we're not witnessing the collision of two simple fluid balls of neutrons, but the collision of two complex geologically structured worlds. Our gravitational wave observatories, LIGO and Virgo, are listening for precisely this. They are sifting through the data from every neutron star merger, searching for this specific acoustic signature. It is a monumental challenge, like trying to discern the exact material of a bell by hearing its chime from 1,000 miles away, through a storm. But the promise is extraordinary. For the first time, we may have the ability to perform geology on an object we can never touch, to probe the internal structure of a stellar remnant light years away by listening to the sound it makes when it dies. The strength of nuclear pasta is no longer just a calculation. It is a prediction, a hypothesis waiting to be confirmed by the echoes of cosmic collisions. And so we arrive at the great humbling chasm that defines so much of modern astrophysics. We have built a beautiful, compelling and mathematically sound picture of this extraordinary state of matter. We can predict its properties, model its behaviour, and foresee its profound influence on the cosmos. But for all its universe-bending power, nuclear pasta remains a ghost in the machine. We are utterly, completely and frustratingly unable to see it. We cannot build a telescope that can resolve the inner layers of a neutron star. Its surface is opaque, a veil of incandescent plasma that hides the secrets within. We cannot send a probe. It would be vaporized by radiation and crushed by gravity trillions of times stronger than Earth's. The very conditions that create nuclear pasta also conspire to conceal it from any direct observation. This is the maddening reality that confronts the scientists on this frontier. They are like detectives who have found intricate, detailed footprints at a crime scene but have never seen their suspect. They are forced to search for clues not at the scene itself, but in the subtle ways the suspect's actions have disturbed the surrounding environment. The search for nuclear pasta has become one of the greatest forensic investigations in the history of science, a hunt for indirect circumstantial evidence scattered across the electromagnetic and gravitational spectrums. One of the most promising lines of inquiry lies in the way neutron stars cool down. A newly born neutron star is unfathomably hot, with temperatures soaring into the trillions of degrees. It cools primarily by radiating neutrinos, ghostly particles that can stream out from its core. The rate at which these neutrinos escape, and thus the rate at which the star cools over millions of years, is incredibly sensitive to the state of the matter they must pass through. The ordered complex structures of nuclear pasta, its tunnels, sheets and bubbles, would interact with neutrinos differently than a simple, uniform liquid of neutrons and protons. It would alter the star's thermal conductivity and neutrino opacity. Models that include a thick pasta layer predict a slightly different cooling curve, a subtly different relationship between a neutron star's age and its surface temperature. We cannot watch a single neutron star cool for eons, but we can take thermal snapshots of hundreds of them across our galaxy, all at different stages of their lives. By plotting their temperatures against their estimated ages, we can build a collective cooling history of their kind. If we find that the observed temperatures of these stars consistently match the predictions from models that include nuclear pasta, it becomes a powerful piece of supporting evidence. It's akin to proving the existence of an ancient civilization not by finding their city, but by analysing the unique chemical composition their industrial runoff left in polar ice cores thousands of miles away. It is a delicate, painstaking process, fraught with uncertainty, yet it is one of our best hopes. Another subtle clue may come from the glitches of pulsars. Many pulsars, which are rapidly spinning neutron stars, exhibit a remarkably stable rotation rate, their lighthouse beams of radiation sweeping past Earth with the precision of an atomic clock. But occasionally and without warning they glitch. The star's rotation suddenly and inexplicably speeds up by a tiny fraction. The leading theory is that this is due to a transfer of angular momentum between the superfluid neutrons in the core and the solid outer crust. The superfluid rotates slightly faster than the crust it is contained within. As the crust slows down, the drag between the two builds until something gives way and momentum is abruptly transferred, spinning the crust up. The nuclear pasta layer lies precisely at the interface between the superfluid interior and the solid crust. Its geometric structure would act as the crucial mediator of this interaction. The way the superfluid vortices pin to the pasta, the way they snag on the spaghetti-like strands or lasagna-like sheets, would determine the amount of stress that can build up and the way it is released. The existence, thickness, and even the specific shape of the pasta could dictate the size and frequency of these glitches. By studying the glitch behavior of thousands of pulsars, we can look for statistical patterns, for families of glitches that can only be explained if such an exotic mediating layer exists. We are, in effect, trying to understand the geology of an alien world by studying its earthquakes from light years away. And finally, we return to the gravitational waves. The detection of a merger in 2017, an event named GW17087, gave us our first tantalizing glimpse into this realm. The signal was a masterpiece of cosmic information, but it was also noisy, and our detectors were at the very limit of their sensitivity. Within that data, scientists are still hunting for the specific high-frequency signature of a stiff crust. Current analysis has placed some constraints, ruling out the most extreme soft models of neutron star matter. But the definitive proof, the smoking gun signal that screams pasta, remains elusive. It may be that we need more sensitive instruments, the next generation of gravitational wave observatories, to truly isolate this subtle effect from the overwhelming roar of the merger itself. Each of these methods provides a single, flickering candle in the immense darkness that shrouds the neutron star interior. None, on its own, is definitive proof. The cooling curves are subject to uncertainties about a star's age and distance. The pulsar glitches could be influenced by other complex magnetic or superfluid dynamics. The gravitational wave signals are buried in cosmic static. The evidence is entirely circumstantial, a cosmic breadcrumb trail leading to a fantastic conclusion. But when taken together, a consistent picture begins to emerge. It is a picture of a star held together by an unseen skeleton, a star whose fevers are cooled by passage through bizarre nuclear geometries, a star whose final scream is shaped by the strongest material in the universe. To truly confirm it, to drag this ghost out of the machine and into the light of established fact, we need more than just clever forensics. We need a new way to listen, a new way to see. And so, the theoretical blueprints for this impossible material exist, sketched out in the language of quantum physics. But a blueprint is not proof. It is a ghost, a tantalizing whisper of a substance so profoundly alien that it challenges our very definitions of matter. To give this ghost a body, to prove that nuclear pasta is not merely a fever dream of theoretical physics, we must leave the clean rooms of our minds and venture into the chaotic cosmos. We must find a way to reach across quadrillions of kilometers of sterile vacuum and somehow impossibly touch the crust of a dead star. How do you prove the existence of something you can never hope to hold? Something forged in a furnace so extreme it makes the core of our own sun seem like a gentle hearth? The answer, it turns out, is not to build a bigger telescope to see it, but to build a better universe to understand it. Our first laboratory is not one of glass and steel, but of silicon and light. It exists within the silent humming sanctums of our most powerful supercomputers, digital realms where the laws of physics are the only bedrock. Here, in these computational crucibles, we can do what nature forbids us from doing on Earth. We can build a neutron star from the ground up. The process is a masterpiece of digital alchemy, a painstaking effort to simulate the unimaginable. We begin not with matter, but with mathematics, feeding the machines the fundamental rules of engagement for the universe. The unyielding grip of gravity is described by Einstein's general relativity, and the bizarre, intimate dance of particles dictated by quantum mechanics. Inside the computer's core, we gather a colossal mass of virtual neutrons, squeezing them together with computational force that mirrors the gravitational collapse of a dying star. As the pressure climbs to levels that defy all terrestrial analogy, we watch. We witness the simulation birth the very conditions of the neutron star crust. Protons and neutrons, no longer content in their familiar atomic arrangements, are crushed into a single seamless fluid. And then, as we descend deeper into this digital star, into the precise region where theory predicts the pasta should form, we see the miracle unfold. The two most powerful forces in the universe, the strong nuclear force binding nuclei together and the electromagnetic force pushing protons apart, engage in a titanic struggle for dominance. It is a war fought on a femtoscopic scale, and the simulation renders its geometry with breathtaking clarity. First, isolated spheres of nuclei, the Nocky phase, appear suspended in a sea of free-flowing neutrons. Deeper still, as the pressure mounts, these spheres are squeezed and distorted, fusing together to form long, elegant strands of nuclear matter, the spaghetti. The simulation continues its descent, and the spaghetti strands themselves begin to merge, forming vast, undulating sheets, a perfect digital representation of lasagna. This is more than just creating a picture. The true power of these simulations lies in their ability to test this digital matter. We can poke it, we can stretch it, we can shear it. We subject the virtual pasta to every conceivable stress, treating it not as a static image but as a dynamic, living material. How does it vibrate? When subjected to immense rotational forces, does it crack and shatter like a brittle solid, or does it flow and deform like a viscous liquid? How easily does heat travel through its bizarre labyrinthine structures? Each of these questions provides a critical data point, a specific, predictable property. The simulations gift us a set of unique fingerprints, a behavioral profile for nuclear pasta. They tell us that if this substance truly exists, it should be the strongest material in the universe by orders of magnitude, capable of withstanding stresses that would vaporize diamond. It should possess unique elastic properties, a specific crunchiness and springiness, all its own. These are the clues we must now hunt for in the wild. The simulations have given us a suspect. Now, we must find matching fingerprints at the cosmic crime scene. Our search begins with the most reliable timekeepers in the cosmos, pulsars. These are the spinning neutron star corpses we have come to know, lighthouses sweeping beams of radiation across the galaxy with a regularity so precise it rivals our best atomic clocks. For decades, we have used these celestial metronomes to test the limits of physics, their steady pulse a comforting rhythm in the cosmic symphony. But sometimes, the rhythm breaks. Without warning, a pulsar will suddenly and inexplicably speed up by a minuscule fraction, a phenomenon astronomers call a glitch. It is a tiny hiccup in its otherwise perfect rotation, a celestial heartbeat skipping a beat before settling into a new, slightly faster rhythm. For years, the cause of these glitches was a profound mystery. The leading theory painted a picture of a star with a complex inner life. A solid, crystalline outer crust spinning at one speed, and a vast, superfluid interior, a frictionless quantum liquid spinning slightly faster. The two are largely decoupled, a liquid core inside a solid shell, but they are not entirely separate. This is where our suspect, nuclear pasta, enters the scene. The pasta layer would lie precisely at the boundary between the solid outer crust and the superfluid interior. It acts as the ultimate interface, the gear connecting the star's two major components. The simulations we run in our digital forges tell us that the pasta's structure, with its tangled spaghetti and layered lasagna, could be incredibly effective at pinning the superfluid. Vortices within the frictionless fluid could become snagged on the nuclear structures, forcing the superfluid to slow down and spin with the crust. But this connection can only hold so much strain. As the superfluid core naturally tries to spin down more slowly than the crust, immense stress builds up in the pasta layer. Finally, a critical threshold is reached. The pasta, this universe's strongest material, shatters. In a cataclysmic starquake, the stored energy and angular momentum are violently transferred from the superfluid to the crust. The vortices unpin, and the crust is kicked into a faster spin. We see this as a glitch. The timing, the magnitude, and the recovery from these glitches are all dictated by the precise material properties, the strength, the elasticity, the breaking strain of the layer that's shattered. Our supercomputer models of nuclear pasta predict these properties with increasing accuracy. Every glitch we observe becomes a new test, a new data point to compare against our virtual material, bringing us closer to confirming the nature of this hidden interface. But glitches are not the only fingerprint we hunt. The very shape of a neutron star could betray the secrets of its crust. While we often imagine them as perfect spheres, the immense forces at play could theoretically support imperfections. Not mountains of rock and ice like we have on Earth, but tiny deformities in the crust perhaps only centimeters high. On a normal object, such a small bump would be insignificant. But on a neutron star, where gravity is 200 billion times stronger than on Earth, a centimetre-high mountain would contain the mass of a terrestrial mountain range. It would be a colossal concentration of mass, a gravitational anomaly. Only a material of almost inconceivable strength could support such a structure against the star's own crushing gravity. Normal matter would be flattened instantly, but nuclear pasta could do it. Our simulations suggest its indomitable structure could sustain these stellar mountains, turning a spinning neutron star into a slightly asymmetrical object, a gravitational gyroscope that is ever so slightly off balance. A perfectly smooth spinning sphere is silent in the language of gravitational waves. But a lumpy one, a star with a mountain, should produce a continuous faint hum. It would be a persistent monochromatic gravitational wave signal, a pure tone broadcast across the cosmos, betraying the asymmetry of the star that creates it. For years, our gravitational wave observatories, LIGO and Virgo, have been listening for this hum from known pulsars. So far, they have heard only silence. But in science, a null result is not a failure. It is a constraint. The silence tells us that the mountains on these stars, if they exist, must be smaller than a certain size. This, in turn, places an upper limit on the strength of the neutron star crust. It tells us that while the crust is fantastically strong, it is not infinitely so. This observation directly confronts our theoretical models. It allows us to discard the simulations that predict a nuclear pasta that is too strong, refining our understanding and narrowing the field of possibilities. We are closing the net. The clues so far have been subtle, inferred from tiny irregularities in rotation and the deafening silence of the gravitational wave spectrum. But on August 17, 2017, the universe decided to provide us with the most violent, most spectacular, and most revealing test imaginable. On that day, two neutron stars, locked in a death spiral for billions of years, finally collided. The event, catalogued as GW-17, sent a tsunami of gravitational waves rushing through the cosmos, a signal that was captured by the LIGO and Virgo detectors. For the first time, we had a front-row seat to the ultimate stress test of nuclear matter. As these two city-sized objects, each more massive than our Sun, spiraled towards each other at nearly the speed of light, they were subjected to tidal forces of unimaginable power. They began to stretch and deform each other, their spherical shapes distorted into something more akin to teardrops. This process of tidal deformation is not instantaneous. It depends entirely on the internal composition of the stars. A star with a soft, pliable interior will deform easily, while a star with a rigid, unyielding structure will resist. The squishiness of the star, its tidal deformability, leaves a direct and unmistakable imprint on the gravitational waveform. It is encoded in the final, frantic moments of the inspiral, in the rising pitch and frequency of the gravitational wave chirp. As we analyse the signal from GW-170817, we were, in effect, performing a seismic survey of a neutron star's interior from 130 million light-years away. The data that poured in was exquisite. It allowed us to measure this tidal deformability with astonishing precision, and what it told us was profound. The neutron stars that collided that day were not infinitely rigid. They had a certain give, a certain softness. This single measurement allowed us to strike a red pen through entire families of theoretical models for the neutron star equation of state. Models that predicted an interior that was too stiff were ruled out. Models that predicted an interior that was too soft were also ruled out. We were left with a narrow band of possibilities that perfectly described the behaviour of matter at these supreme densities, and nestled comfortably within that band are the very models that predict the existence of a complex structured nuclear pasta layer. The gravitational waves from that ancient collision carried a ghostly echo of the pasta within. We couldn't see the gnocchi or the lasagna directly, but we witnessed how the star as a whole behaved because of their collective strength and structure. It remains the most powerful piece of circumstantial evidence we have ever found. The investigation continues on multiple fronts, each new observation adding a small but crucial piece to the grand puzzle. The way a neutron star cools over millions of years, for instance, is heavily dependent on the thermal conductivity of its crust. A tangled pasta layer might trap heat differently than a simple crystal, leading to a cooling curve that we could potentially observe in aging neutron stars. The colossal energy releases from magnetars, a type of neutron star with an insane magnetic field, are thought to be caused by massive fractures in the crust. The energy unleashed in these events, some of the most powerful flares in the universe, is a direct function of the crust's breaking strain. Understanding the mechanical failure point of nuclear pasta is therefore key to understanding these exotic phenomena. Each magnetar flare becomes another natural experiment, another chance to glimpse the properties of the material that lies just beneath the surface. We stand at a remarkable precipice. We have our digital blueprints, forged in the virtual cores of supercomputers, which give us the suspect's detailed profile. We have the tantalizing clues from the cosmos, the rhythmic skips of pulsars, the profound silence where gravitational hum should be, and the spectacular waveform-shaping death throes of colliding stars. None of these observations is a smoking gun on its own. None provides a direct photograph of this alien matter, but when viewed together, the web of circumstantial evidence becomes extraordinarily compelling. The data from the heavens and the predictions from our simulations are beginning to converge on a single astonishing conclusion. The universe is telling us a story, and the language it uses is one of gravitational waves and gamma-ray flashes. We are finally learning how to translate it. The next glitch, the next merger, the next burst of energy from a dying star could be the one that turns this powerful inference into undeniable fact, confirming that deep inside these celestial tombs lies a strange and beautiful architecture that is the true, undisputed champion of all matter. And so, our long descent into the heart of a fallen star concludes. We have journeyed from the quiet halls of theoretical physics, where the very idea of nuclear pasta was first conceived as a mathematical ghost, to the violent, chaotic aftermath of a supernova, the cosmic crucible where it is forged. We have navigated a landscape of bizarre gravity-sculpted geometries, from the humble spheres of gnocchi to the continent-spanning sheets of lasagna, each layer a testament to the unimaginable pressures reigning deep within a neutron star's crust. This voyage was not merely an exploration of a strange material, it was a confrontation with the absolute limits of nature, a place where the familiar rules of matter are not just bent, but shattered and reassembled into something profoundly alien. What we have uncovered is more than just a curiosity for the astronomical catalogue. In the tightly bound structures of nuclear pasta, we are granted a rare, intimate look at the universe's ruling council, the fundamental forces, locked in a desperate and eternal struggle. Here, the electromagnetic force, which relentlessly tries to tear protons apart with its repulsive power, is finally and utterly overwhelmed. It is subjugated by the unyielding grip of the strong nuclear force, the most powerful interaction in nature, which binds nucleons together into these impossibly dense configurations. This is not the gentle balance we see inside the nucleus of an atom on Earth. This is a raw, brutal dominion. Gravity, the architect of this entire celestial object, acts as the ultimate enforcer, a relentless compressor that provides the very conditions for this nuclear drama to unfold, squeezing a sun's worth of mass into a city-sized sphere and igniting this strange alchemy. By studying this material, we are essentially eavesdropping on the most extreme conversation between the universe's fundamental laws. We see how their hierarchy can shift, how their power dynamics can be completely inverted under conditions so far removed from our own experience. Nuclear pasta becomes a cosmic laboratory, a unique specimen that allows us to test our theories of quantum chromodynamics and nuclear physics in a regime that we could never hope to replicate on Earth. It is a physical manifestation of equations that would otherwise live only on a blackboard, a bridge between the abstract world of pure mathematics and the tangible, violent reality of the cosmos. It teaches us that the forces that govern our existence, from the light of our sun to the stability of our own bodies, are capable of behaviours we're only just beginning to comprehend. The universe, it seems, has a far richer and more complex imagination than we do. This journey also forces us to fundamentally redefine what a material can even be. On Earth, the strongest substances we know, graphene, diamond, carbon nanotubes, derive their strength from the delicate, precise arrangement of electron bonds between atoms. They are marvels of chemistry. But nuclear pasta operates on an entirely different plane of existence. Its integrity comes not from chemistry, but from the raw, unshielded power of the strong force itself. There are no atoms here, no electron shells dancing in orbital patterns. There are only protons and neutrons crushed together into a single, monstrous quantum mechanical entity. To compare its strength to that of steel is like comparing the gentle lapping of a wave to the cataclysmic impact of a planet-killing asteroid. The numbers become so vast they lose their meaning, a testament to a substance 10 billion times stronger than anything we have ever engineered. This isn't merely a contest for a cosmic record. The properties of this material have profound consequences for the life and behaviour of the neutron star itself. We have seen how the lasagna-like layers could support colossal mountains, perhaps only centimetres high, yet so massive they could radiate gravitational waves continuously, acting as a cosmic hum we might one day detect. These subterranean pasta structures could explain the enigmatic glitches we observe in pulsars, where the star's crust suddenly cracks and settles under immense strain, causing a fractional but detectable jump in its rotation speed. It's a form of celestial tectonics, where the shifting of nuclear continents creates a star quake that reverberates across the galaxy. The pasta layer also profoundly influences how the star cools over millions of years, acting as a barrier to heat transport and neutrino emission, a thermal blanket woven from the strongest threads imaginable. The cooling curve of a neutron star, which we can observe with our X-ray telescopes, is therefore a direct fingerprint of the exotic physics happening deep within its crust. We are no longer just observing a distant point of light. We are performing stellar archaeology, diagnosing the internal state of an alien object by taking its temperature from light years away. The discovery and confirmation of nuclear pasta should fill us with a profound sense of humility and wonder. for it is a powerful reminder of how much of the universe remains hidden in plain sight. For decades, neutron stars were modelled as simple, uniform spheres of degenerate matter. We now understand that their interiors are layered, complex and dynamic worlds, home to phases of matter that defy our terrestrial intuition. If such an extraordinary substance can exist within the crushed remnant of a common star, what other wonders lie concealed in the cosmos's dark corners? What exotic states of matter might lurk within the even more mysterious cores of these stars, where pasta might give way to a quark-gluon plasma, a soupy sea of elementary particles freed from their proton and neutron cages? What secrets are held within the event horizons of black holes, or in the filamentary structures of dark matter that form the scaffolding of the universe? The existence of nuclear pasta is a call to adventure. It tells us that the universe is not a sterile, empty void punctuated by familiar objects. It is a vibrant, creative, and endlessly surprising place. It is a realm where the laws of physics, under the right pressures and temperatures, can behave like a master sculptor, creating structures of breathtaking complexity and resilience. We are just beginning to develop the tools and the theoretical frameworks necessary to explore these hidden realms, to pull back the curtain on phenomena that were once relegated to the domain of science fiction. The universe, it turns out, is the ultimate material scientist, and its creations are far more spectacular than anything we could have predicted. It challenges us to keep looking, to keep questioning, and to be prepared for the unimaginable. This grand challenge is already being met. The future of this exploration is not a distant dream. It is being built right now in the form of next-generation observatories and computational engines that promise to give us an unprecedented view into the heart of a neutron star. The era of gravitational wave astronomy, which we saw began so spectacularly with the detection of merging neutron stars, is still in its infancy. Future detectors, like the Einstein telescope in Europe and the Cosmic Explorer in the United States, will be vastly more sensitive. They won't just register the final, violent chirp of a merger. They will listen to the subtle gravitational whispers emitted in the moments before the collision. As two neutron stars spiral towards each other, their immense tidal forces will stretch and deform their crusts. The precise way in which they deform, the way they ripple and vibrate, will be directly influenced by the properties of the nuclear pasta layer within. Imagine it. By analysing the subtle modulations in a gravitational wave signal, we could perform a kind of stellar seismology from 1 billion light-years away. We could potentially distinguish the signature of a rigid, pasta-filled crust from that of a more fluid interior, effectively feeling the star's structure through the medium of space-time itself. We could measure its resistance to being torn apart, a direct probe of its material strength. These new observatories will also allow us to detect the continuous faint hum of gravitational waves from those tiny pasta-supported mountains on rapidly spinning isolated pulsars. Finding such a signal would be a monumental achievement, a direct and unambiguous confirmation of these exotic geological features. It would transform pulsars from being mere cosmic clocks into dynamic, vibrating objects whose internal structure we can finally map. Our radio and X-ray telescopes are also poised for a revolution. The Square Kilometre Array, or SKA, will be the most sensitive radio telescope ever built, capable of monitoring thousands of pulsars with breathtaking precision. It will allow us to time their rotational glitches with such accuracy that we can begin to build detailed models of how the crust and the superfluid core interact, how stress builds up in the pasta layers, and how it is catastrophically released. Simultaneously, next-generation X-ray observatories will track the cooling of young neutron stars with far greater fidelity. By gathering more precise temperature data over longer periods, we can refine our models of heat transport through the crust, providing much tighter constraints on the thermal conductivity of the gnocchi, spaghetti, and lasagna phases. Each new data point, whether from a gravitational wave, a radio pulse, or an X-ray photon, will be another crucial piece of the puzzle, helping us to home in on the true equation of state for matter at its most extreme. Yet, observation is only half of the story. The quest to understand nuclear pasta is also driving a revolution in theoretical and computational physics. The simulations we have witnessed, which require some of the most powerful supercomputers on the planet, are still making approximations. A truly complete picture would require us to model a far greater number of protons and neutrons, incorporating not just nuclear forces but also the subtleties of general relativity, the hydrodynamics of the neutron superfluid, and the complexities of magnetic fields all at once. This is a computational Mount Everest, a challenge that will push the boundaries of our processing power and our algorithmic ingenuity for decades to come. As our computers become more powerful, moving from pettascale to exascale and beyond, our virtual laboratories will become ever more realistic. We will be able to simulate larger volumes of the neutron star crust, capturing the subtle, long-range correlations that define the transitions between different pasta shapes. We will refine our understanding of quantum mechanics in this high-density environment, solving the complex many-body problem with increasing accuracy. The ultimate goal is to create a complete multi-physics model of a neutron star from its core to its atmosphere, a digital twin that evolves and behaves just like its real-life counterpart. With such a model, we could crash virtual stars together, trigger virtual starquakes, and cool virtual crusts, comparing the results directly with our observational data. It is through this intricate dance between theory and observation, between the silicon brains of our supercomputers and the vast lenses of our telescopes, that the final secrets of nuclear pasta will be unlocked. Each side of this endeavour informs and inspires the other, pushing us closer to a complete theory of dense matter. And so, we stand at a remarkable threshold. The journey into the world of nuclear pasta is a story of human curiosity at its most tenacious. It began with a question whispered among physicists: what happens when you push matter too far? It led to decades of painstaking theoretical work, complex calculations, and a deepening suspicion that the universe harboured a state of matter beyond our wildest imaginings. Now, through the echoes of cosmic collisions and the faint light of cooling stellar embers, we are finally gathering the evidence to confirm its existence. We are beginning to chart the geography of a world hidden within a world, a realm of nuclear mountain ranges and subterranean plates governed by forces that dwarf our comprehension. This quest teaches us something profound about our place in the cosmos. It reveals that even the most violent and seemingly simple objects, the dead remnants of stars, conceal a richness and complexity that can occupy our greatest minds for a lifetime. The universe does not give up its secrets easily. They are encoded in the faintest of signals, hidden behind veils of unimaginable density and distance. But with creativity, with persistence, and with an unyielding desire to understand, we can learn to read that code. We can build the instruments and the theories necessary to translate the language of the cosmos into human understanding. As you look up at the night sky, remember what lies hidden within some of those faint points of light. Remember the fallen stars, the city-sized atoms that are the tombstones of once mighty suns, and remember that deep within them, the very fabric of matter has been crushed and reforged into the strongest material in the universe. A substance born of impossible pressure, held together by the most powerful force in nature, a testament to the boundless creativity of the cosmos. The story of nuclear pasta is far from over. In truth, it has just begun. And its continuation promises to reveal even deeper truths about the fundamental nature of our reality, inspiring us to continue our endless, incredible journey into the unknown.